Hello friend, welcome to my YouTube channel Electrical Boost. In our previous video, we understood what do you mean by the biasing, what is the DC load line, how Q point is decided, where the fixed bias is not suitable for the real circuit. So that today we are going to discuss what is the importance of voltage divider, another biasing method that is called voltage divider biasing. Voltage divider, this is the most important biasing. Why this is most important? Because in this we can get stable Q point, stable Q point, okay, and less dependency on transistor beta value, or you can say HFE value, and also temperature stability, okay. So we're going to discuss how it will form. In the voltage divider, we added two divider network, that is R1 R2 in the base. Here we are going to give the input. Here we are going to input what are the required to amplify, okay. Here we are getting the output, okay. First we know describe how it will come, okay, how it will design, okay. First we need to find, for finding this IC, here it coming that current is IC, here is the IC, here is the IV, here is the IE. For finding this stable point, first you need to find this IV value, okay. Let assume this is R1 R2 and RC RE, okay. For finding this IV, it's directly not possible, so that what we doing, we split this network, okay. This is this section, okay. If I split then the VCC also here, this VCC also both are in short so that VCC you can take like this. So I going to apply here one theorem, circuit network, that is Thevenin's theorem. In our you can go previous video or some video in our link, you can go check and what is the Thevenin's theorem, okay. Basically you know Thevenin's theorem. First I split, means I need to find what much voltage or current here IV coming, so that we go how I split the circuit. I can modify this circuit to like this. How? Here is the VCC, okay. I put like that VCC. Here is the R1, okay. Here is the R1, and here is the R2, and this is the terminal. I can name as AB, where this connected to the base of the this one you can see here, this one, okay, this point, and this is the ground, okay, here. So here our objective to find first what is the, here we need to find the RTH, Thevenin's resistance. What is the RTH value here? While condition the RTH, that time what you do, we need to, while finding the source should be deactive, means VCC will be going to short circuit, so that it will short. If it is short, then what happen, then from this side we can find RTH equal to, both are parallel, So RTH equal to R1 into R2 divided by R1 plus R2. Okay, this is the RTH. Then if you go for the VTH, then VTH means you can find here. VTH is this value here. From here you can find VTH equal to voltage drop across this R2. The VTH is equal to VCC. You can put the voltage VCC into R2 divided by R1 plus R2. R1 plus R2. Here you found those two equation, that is the VTH value you get, okay, and another one you get the RTH. Next we're going to put this Thevenin's equivalent circuit. Thevenin's equivalent. This Thevenin's equivalent circuit, how it will come? The circuit is look like this. This is VTH, okay. This is RTH. This is A and B. Now we are going to put this circuit to here to simplify this IV. Okay. If I put this Thevenin's equivalent circuit to this will look like this. Okay. Okay. So here the IB. For finding the IB, we need to put KVL. We need to put KVL in the circuit. You know this voltage across this. This is VBE. Take as this is VBE. This take as VBE. Means here the voltage drop across the base and emitter. Okay. So I going to apply. Then how this KVL? VTH, okay, minus IB into RTH, okay, then minus VBE, okay, then here is the IE. Here current is IE, so that minus IE into RE. You already know in the previous video that IC equal to beta IB, okay, and I equal to IB plus IB plus IC. So that final I equal to can be written like this: IC IB plus beta IB. So I can write like this: IB, take as common 1 beta plus 1. I can write like this. So I put this one to here. So the final will come like this, that here wait, this VTH minus VBE, I can write like this, minus IB RTH, okay, then I put this value minus IB into beta plus 1. From this I going to find the IB equal, this is equal to 0, sorry, equal to 0. Then IB equal to, final get IB equal to VTH minus VBE divided by RTH plus beta plus 1 into RE. This is the final value of IV. This is the final value of IV. Okay. Suppose I want to find final IC. Okay, IC, you can see here IC equal to how much? You know already, beta into IB. So that IC equal to, from here IC equal to this complete into beta, means like this, beta into VTH minus VBE RTH plus beta plus 1 ARE. Okay, if you see, if you RTH is less than much more less than the beta B plus 1 into RE, then the system will be stable. Okay, this is the equation here we are getting. Then another one, here we need to find the VCE. What is the, while finding the load line, VCE. How to find the VC? Here you see VCC, you need to find this voltage VCE equal to that VCC minus, you can put like this, IC, single current IC into RC plus RE, because IB is too small. Okay, this is the VCE. Using those equation, we're going to check how in the beta changing, how it is stable behaving. Okay, we just give you an example and we check how it is changing. Okay, now it is through this RTH, it will be controlled. Okay, if RTH is too less, then as compared to this one, then it will be stable. Okay, we're going to check with a real example. This is the one circuit where we can going to find and check the how it will stable occur. Here you see all value already the design. Okay, we're going to check, and here we will conclusion how it will design. Okay, and this VB here, VB is equal to 0.7. basically it is 0.7 because the silicon maximum use, otherwise 0. The data sheet also mention how was that VBE. Okay, first we know already that VTH equal to, we're not going to implement all thing here, previously you know, so that I will need to find this IB first. Okay, then we already know IB equal to how much? IB equal to VTH minus VBE divided by RTH plus beta plus 1 into RE. Okay, for this we need to require the VTH and RTH. Okay, so we need to find that VTH value. Here VTH equal to, okay, VTH equal to this 2. Okay, VCC equal to 12 volt. We know that VCC into this 2K 2 divided by 2 plus 10. Okay, this is will become RTH equal to 12 into 2 divided by 12. This is 2 volt. Okay, this is VTH, and RTH equal to this is 10K parallel with 2K. This is will come 1.66 kilo ohm. Okay, then we put this value to here, so we get we put this value IB equal to VTH is how much? 12 minus VTH is 2 volt minus 0.7 divided by RTH 1.66K into plus beta equal to 50 plus 1 into how much? 1K. Okay, then we get finally IB equal to 24.6 microampere. 24.6 microampere. Then we need to find that IC value. We're going to find that IC value. IC equal how much? If IC equal to beta into IB, then it will come like that: 50 into 24.6 microampere. Then we'll get 1. Already calculated, so that 1.34 milliampere. Okay, this is the IC value. Next we need to find that what is the VCE value. That is equal to VCC minus IC RC plus RE. That is how much? I put this value: VCC equal 12 minus 1.234 milliampere. RC is how much? 3.6 plus 1, 3.6. Okay, then I get total 6.32 volt. Suppose if I go for that DC load line, you can check. I draw the DC load line for checking the stable point. I already have the VC and IC. So here this is the VC. Okay, here the point is VCC. Okay, this is the IC. Okay, this line we get this is the load line. Okay, this is the maximum. This is VCC by RC plus RE. Okay, here somewhere I get VCEQ means 6 point, how much? Get 6.32 means half of this one, which is 12, almost half. So I get somewhere here 6.32, and here I got that how much? 1.234 milliampere. 1.234. Okay, then I got here only. Then it is perfectly stable. Suppose I change this beta to 100. Suppose let 100 means it will 100 time it will increase, 100% it is increase. Then we check what is the value. If I going to change, this is to 100. Okay, here first we need to check, find this value. Okay, VTH is same because that RTH same. Okay, next you can see that VTH also same and RTH also same, so that we put here with new value. Okay, suppose for 100, okay, for beta equal to 100, then it will come IB equal to, already put this value, and I get this value is 12.6 microampere, 12.6 ampere new for 100 meter. So then the IC will be new IC will be IC equal to beta into IB, the 100 into 12.6 microampere, that is equal to 1.26 milliampere. 1.26 milliampere. Okay, then we're going to find that VC with new value. VC is equal to VCE. VC equal to VCC, sorry, that VCC means we can put this value here, 12 minus 1.26 into 36 point plus 1k most equal to this value, only 1.26 to 1.234. okay, you can see here, if I change the beta up to 100%, only small value it will be changed, small value that maybe for the new it will come like this, 1.26 and this value, small change. When you change the 100% of beta, that time it will small variation in the stable point. So this method is best suitable for that practical design. okay, thank you for watching this video. Please like and subscribe my channel. Thank you.